Okay. So now the question is to find the average force between the two cores. Okay. So now to get this force, we need to cut here. We need to take A alone or B alone. For example, if I take A alone, okay? For A, what do I know? I can now draw the impulse and momentum diagram. It can help me in my solution. So initially, I know the initial velocity. So in the initial momentum diagram, I just draw vector MA, VA initial. Okay? Now, plus the impulse diagram. In X direction, the only force doing impulse is the action of B on A. So it's F of B on A. And since they asked for an average force, the impulse of the force is integral F from 0 to 0.8 seconds dt, okay? But here, they asked me for an average force. Because why? Because I don't know how F is varying with time. This is why they asked for an average force of B on A. So I can replace this integral by F average times delta T. So this is the impulse diagram in X direction. Of course, I have other forces, but in Y direction, you can present them. You have the weight and you have the normal, but they are non-impulsive. You have integral W dt. You can consider them because you know the time. Since you know the time of application, you can consider them. You can say that this impulse is W delta T. And it will be cancelled out by the impulse of the normal. Here, it's equivalent to apply some of forces in Y direction equal to 0. They will not have any effect on X direction. They will cancel each other in Y. So in X, we just have the interaction between A and B, okay? And in case you have friction, they should give you the kinetic friction coefficient, then you can put minus mu k and delta T, okay? But here, they didn't mention anything, so you can consider the friction to be negligible, okay? And even because the time also is it's a short time, the impulsive force will be dominant over any other force, okay? So even if you have friction, you can say it's non-impulsive force, so I can neglect its effect compared to the impulsive force of the collision between A and B. Equals to the final linear momentum. At the final state, you have...
Doctor?
Yes? You have...
Yes, I have a question about the friction.
Yes.
Is there any friction that is related to FAB?
No, because here you have a smooth contact between...
Not here, in general.
In general, yes, very important question.
There is a rough...
yes, if you have rough surfaces, you will have a normal force, okay? And then this force is impulsive. Why it's impulsive? Because if you have a friction force, it will be related to F. You know that in general, how you calculate the friction, it's a mu k.
Normal times mu k.
Yes. If you have sliding between the two, you have a mu k. If not, let's say it's static friction, for example, and it's the extreme static friction, it's a mu Sn, for example. Okay. So, and what is N here? N, it's not this N. It's the normal reaction between A and B. So it's mu times F. F of B on A. And because F is impulsive, this friction will be impulsive. So you cannot neglect it. Okay. So this is why I told you if you have a force related directly to an impulsive force, it's impulsive. So in case it's a rough surface, you need to consider the friction, and you cannot neglect it because it will be an impulsive force since it's proportional to FB on A, which is impulsive. Okay.
Okay, we consider FBA and the friction in this case.
Yes, exactly. Okay. But since they didn't mention anything, we consider a smooth contact. and we just have this force. Anyway, even if you have it here, it's in y direction, and it will not affect your equation in x, okay? But it will affect your equation in y, okay? So now, once we draw the diagrams, we can apply the principle of linear impulse and momentum along the x direction. So what can we write? We can write plus MA VA initial in x minus F average. Why minus? Because the impulse, how we know this? Here we know this because it's by due to collision, okay? A will push B in this direction and B will push A in the opposite one. If we are not sure about the direction, we can assume it. And then if we get positive results, the assumption is right. If we get a negative result, the assumption is wrong, okay? So minus F average times delta t. Delta t is given 0.8 seconds equals MA times VA final. You see the importance of the first step in it. Sometimes they will not divide the question for you. They ask you directly the second question. They can ask you directly, find the average force between the two cars. But you cannot start directly with taking A alone, because if you take A alone, you have two unknowns, F average and VA final. So you need another equation. That's why you say, let me first take system A plus B. When I take system A plus B, I have one unknown because F average will be internal. I solve for VA final. And once I get VA final from conservation of linear momentum, I can take A alone to find F average. Okay? If you take B as system, it's exactly same approach. But now if you take B, you take F to be opposite, because the action of A on B is opposite to the action of B on A. So if you take B as a system, your average impulsive force will be acting in positive direction. Okay? So you can take B as system and your equation will be plus MB VB initial plus F average times delta T. So plus F average times 0.8 equals to, if you didn't use the conservation of linear momentum, you can use the system of equations. You get two equations with two unknowns. You can solve for VA final and for F average. Anyway, guys, if you add the two equations, if you add them, what do you get? You will go back to conservation of linear momentum, because the impulses will cancel out. So these two will cancel out, and you will end up with sum of initial linear momentum equals to sum of final linear momentum. And because V final is common, you can take it into factor. Okay, clear? Any question on this problem?
Doctor, can you please repeat what you just said, because I didn't hear you?
Okay, which the final step you mean?
Yes, when we were talking about M plus MB, why you were adding them up?
Okay, I am telling you that if you add them up, you obtain back the conservation of linear momentum. No need to add them up here, okay? You can write these two equations and solve them. You get two equations, two unknowns. But in case you want to see why these two equations will take you back to the conservation of linear momentum, when you add them up, it's like you are considering system A plus B. So when you take system A plus B, what will happen? The impulses will be internal, and they will cancel each other, plus minus, because of action reaction, okay? So when you take A plus B, you end up with conservation of linear momentum, because you are summing here linear momentum at initial state equal to summation of linear momentum at final state. So I am showing you that at the end, you need to write two equations, and any combination of the two equations will get you to this, will take you to the third. or you take A alone, B alone. You write two equations with two unknowns and you solve for VA final and F average. Or you can start by the conservation of linear momentum, which is actually the addition of these two equations. You get VA final. And once you get VA final, or you take A as system, or you take B as system. Okay?
Yes, clear. Can I ask one more question, please?
Yes, sure.
When we were doing the exercise with the pulleys, you talked about friction. Can you tell us how we can represent it if we do have friction on a pulley?
Look, it's really complex because it will have variable direction. Let's say your cord is turning in this way, okay? Friction will oppose rotation, let's say. So you will have to get the total friction, you need integration because you need to project, okay? The friction force is varying in direction, so you need to project in X and Y, and you need to perform integration. It's not straightforward, okay? It's a little bit complex. So we'll always have frictionless pulleys, but just you should keep in mind that in case you have friction, this might affect the tensions.
Okay, thank you.
Okay.
Do we face this case where the tension is not the same due to the friction?
No, you don't, but you will have after, okay, when we study, if you want, the case of a rigid body, so the pulley will have a certain inertia. If you don't neglect the mass, you will have a certain inertia, okay? And if you have an inertia for your pulley, summation of moment will not be zero anymore. It will be equal to inertia times alpha, and then the tensions will not be the same from both sides. So in case your pulley is not massless, you cannot say that the tension is the same. But in case you deal with massless and frictionless pulleys, you can consider that the tension will be the same. We'll consider the case of non-massless pulleys after in future chapters. Okay?
Okay, doctor, thank you.
Another problem. Two cars A and B each have a mass of 150 kilogram and are costing with the velocities shown before they freely collide head-on. If no energy is lost during collision, determine their velocities after collision. What do we mean by this sentence? This means that because of collision, you don't have any losses. So the total kinetic energy before is equal to the total kinetic energy after. This is what we call elastic collision. For an elastic collision, during the accident, you have deformation, but this deformation is not very important. So after the collision, cars will separate from each other and the energy of deformation will be restituted back. So I will not lose any of my kinetic initial energy. So from this sentence, you can say that summation of kinetic energies at initial state, at state 1, equals to summation of kinetic energies at state 2. Okay? And here, what are your unknowns? You want to solve for the final velocities after the accident. Okay? So after the accident, you will have separation of your cars. And here, we can prove that because we'll prove it in equations. What will happen is that since you have the same mass, cars will change direction and they will switch velocities, and we'll prove this from this problem. Okay, so this velocity will have v final minus 2, and this will be v final plus 3. We'll see why. Okay, so we need to solve for v final of A and v final of B. What you can do, you can say, I will assume, I don't know if they will change in direction or not, maybe. Okay, so you can say, I can assume the velocities because I don't know the final direction. I can keep them in the positive direction. And if I get a positive value, this means that my assumption is right. If I get a negative value, this means that my assumption is wrong. So I can deal with it as algebraic value, VA2x. If it's positive, then the direction is along x positive. If I get negative results, so the direction is opposite to x. So since I don't know what will happen, I can assume that the two cars will remain in positive, will have a positive x direction. And according to my solution, I can say if it's right or not. Okay. So VA2x, VB2x will represent the final velocities in x direction. I have two unknowns here. So I need to solve two equations. The first equation is clear because they told me no energy is lost during collision. So summation of kinetic energies at state 1 is equal to summation of kinetic energies at state 2. So equation 1 will be half MA times VA1, which is 3. So times 3 squared, plus the initial kinetic energy of B, so plus half MB times 2 squared. This is the total kinetic energy at the initial state, equals to, at final state, I have half MA VA2x squared plus half MB VB2x squared. Okay, so this is my first equation. I need a second one. Always, whenever you have a collision, okay, when you have a collision, think about taking the whole system and applying conservation of linear momentum, because when I take the whole system, the force of the accident, the collision force, will cancel out by action reaction, and all external forces are non-impulsive. And if you consider friction with the ground, it's non-impulsive compared to the force of interaction between A and B. So when you take A plus B as a system, you can apply conservation of linear momentum. And conservation of linear momentum will tell you that MAVA1 plus MBVB1 equals MAVA2 plus MBVB2, and you are applying it in positive x direction. So here we assumed algebraic values. If VA2 positive, this means that it will be in positive x. If VA2, you get a negative result, this means it will be directed in negative x. So this equation will give you a first relation, the second relation. And then you solve the system of two equations with two unknowns. Let us see the second relation. So here, the second relation is conservation of total energy. Here, you are moving in a horizontal plane, so no variation in gravitational energy. So you only have variation in kinetic. This is why you can say that the total kinetic energy at state 1 is equal to the total kinetic energy at state 2. Here, what is a little bit challenging is that you have a second degree relation. Because you have a second degree equation, you will end up with two possible solutions, okay? But one of the solution will be rejected because the velocities will not change. And what I mean by this, if you take the solution for VB2, you will get VB2 is -2, okay? Is -2 or 3. You have two possible solutions. But if you go back to your given, VB at the initial state was -2. So it's impossible to have the same velocity after the collision. So you will reject this solution and you will opt for the second solution. So of course, when you have one of the possible solution is to have non-change in velocity. Because look, if VA1 equals VA2 and VB1s equal VB2, you will satisfy conservation of momentum and you will satisfy conservation of energy. But this solution is if you don't have anything, if you don't have a collision. So this solution will be rejected and you will select the second solution, which is 3 meters per second. So as we said, VB2 will take the velocity of VA. Yani car B will have the velocity after collision, will have the velocity of A before collision. And we will prove this together by a simple system of equations that I will introduce for you now. So here, VB2 will take the velocity of A before, so VB2 is equal to VA1. While if you consider the velocity of VA2, if you solve, will take the velocity of B before, so VA2 will be equal to minus 2 meters per second. Why we always have this in case you have same mass of particles? Only if you have the same mass. We'll see why. Okay. If you solve this system again in detail, since you have the same mass, both cars here have a mass of 150 kilogram. So your equations will simplify a lot. MA equals MB. This will simplify. So your first equation will be VA1 plus VB1 equals to VA2 plus VB2. Okay? Now, if you use the conservation of kinetic energy, since M is the same, also M will simplify. Okay? And this is equation 1. Equation 2 of conservation of kinetic energy will be half VA1 square plus half VB1 square. M is we will cancel out M because it's the same mass everywhere. So plus half VB1 square equals, and also half, you can take it, you can drop it because you have 0.5 mv square for all of your terms. So you can cancel out also half. So we'll have here VA2 square plus VB2 square, okay? And if you want to solve this system in a simple way, you can say, let me take VA2 to this side and factorize. So I have VA1 square minus VA2 square. You can write it as VA1 minus VA2 times VA1 plus VA2 So this is from the first side. From the other side, okay, you will have VB2 square minus VB1 square. So if you factorize, you get VB2 minus VB1 times VB2 plus VB1. Okay, but look, according to your conservation of linear momentum, you have that from this equation, if I take VA2 to this side and VB1 to the other side, you can say that VA1 minus VA2 is equal to VB2 minus VB1. These two terms are equal. So from conservation of linear momentum, you can deduce that this term will cancel out with this one. They are equal. So your second equation will be VA1 plus VA2 equals to VB1 plus VB2. Okay, and you can transform your system now. Instead of having a second degree equation, you have a set of two linear equations. Okay, all you have to do is to take VB1 to this side and VA2 to the other side. You will get that VA1 minus VB1 is equal to VB2 minus VA1. minus, sorry, VA2. Okay. And now if you add the two equations 1 and 2, what will happen? If you add the two equations, you have plus VB1 minus VB1 will cancel out. So you get that by adding the two equations, 2VA1, and you add the two other equations, VB2 will cancel out. Okay. So you get, just sorry, 1 second. So here it's VB2 minus VA2, and here it's VA1 minus VB1. And from the first equation, you have VA1 plus VB1 equal VA2 plus VB2. So when we add the two equations, VB1 will cancel out, and we'll have that 2VA2 is equal to 2VA2 is equal to 2VB1. Okay. Sorry, 2VA1, because when you add the equation, VB1 will cancel out. So 2VA1 equals 2VB1. 2VB2, sorry. Okay, this means what? This means that the velocity of B after collision is equal to the velocity of A before collision. And if you subtract the relations, and instead of doing 1 plus 2, when you do 1 plus 2, you get 2VA1 equals 2VB2. When you subtract the equations, and if you do 1 minus 2, VA1 will cancel out, and you will have 2VB1. So if you subtract 1 minus 2, you get 2VB1 equals to, when I do the subtraction, VB2 will cancel out, and I will have for the second term, VA2 minus VA2, so 2VA2. So 2VB1 equals to 2 times VA2. So we proved together now that if I have a collision between two cars of same mass, the velocities will be switched. So velocity of B at state 2 will be equal to the velocity of A at state 1. And velocity of A at state 2 will be equal to velocity of B at state 1. So they will switch velocities. And when I solve, I solved here, I got exactly the same result. Okay. Question on this? Now, we can also,
Doctor,
yes?
we can always take it as a rule, yani, when we solve, we can always apply it without the proof it.
You can apply it in case you have this case, yes. If you have the same mass, okay,
Without
and
proof.
elastic collision, yani no loss of kinetic energy, you can say the velocity will switch. Yes, you can apply it.
If plastic collision, we cannot.
If plastic, we cannot. And if different masses, also we cannot.
Of course, of different
But
masses.
if we have different masses, we can also have a simplified form, because
Or elastic.
if you have different masses with elastic, what will happen? Your equations will be MA VA1 plus MB VB1 equals to MA VA2 plus MB VB2. Okay, and now instead of here half, you can for half you can simplify it. You will have here from this side MA VA1 square plus MB VB1 square equals MA VA2 square plus MB VB2 square. Okay. Now you can you will do the same procedure as we did here. So first you can take MA in factors. So you will have here MA times. So MA times VA1 minus VA2 times VA1 plus VA2 equals to, from the other side, to MB times VB2 minus VB1 times VB2 plus VB1. Okay, exactly same procedure, but you don't cancel M. Now, from linear momentum, if you go back to linear momentum analysis, okay, from linear momentum, you can say that if I take, if I consider, okay, the following term. If I take this term to this side, what do I get? I get MA times VA1 minus VA2, okay, equals to MB times VB2 minus VB1. So also you can say that MA times VA1 minus VA2 is equal to MB times VB2 minus VB1. So these two terms will cancel out. So even if you don't have same mass, what will still apply is this equation, that VA1 plus VA2, okay, is equal to VB1 VB2 VB1 plus VB2. Okay, so this will allow you to transform your system from a linear system, from a system with a second degree equation, to a linear system. And what will be your linear system to solve for now? Yani you still can write, okay, you still can write VA1 plus VA2 equals to VB1 plus VB2. And your system of equations now will be the following. Conservation of linear momentum, which is MA times VA1 plus MB VB1 equals MA VA2 plus MB VB2. So this equation, the only difference with the equation of same mass is that the mass will not simplify. And your first equation will be a linear equation, and you have masses, you replace them. But the second equation that will still be applicable, even if the mass are different, are VA1, and we proved it now, VA1 plus VA2 is equal to VB1 plus VB2. And now instead of dealing with a complex second degree equation, you replaced it by a linear equation. So you can solve, so even if you have a non-equal mass, okay, you can, instead of using a second degree equation, you can say, I can replace it directly by this equation, VA1 plus VA2 equals to VB1 plus VB2. And if you want to take your unknown to one side, okay, you can take VB1 to this side because it's known. So VA1 minus VB1. So always, when total kinetic energy is conserved, okay, you can say that VA1 minus VB1 is equal to VA2 minus VB2. This is always applicable if you have same mass or not. But if you have same mass also, the solution of your system will give you that VA1 is equal to VB2 and VB1 is equal to VA2. This is the addition if you have the same mass. But if you don't have the same mass, you can still apply this relation, this linear relation. So instead of having to deal with a second degree equation, it's much easier to deal with a linear equation. And then you will have two equations with two unknowns. You can solve for VA2 and VB2. Okay? Question on this? Okay, so we are done.
No, doctor.
We are done for today. Bye bye.
Thank you, doctor.
Welcome.
Doctor,
Yes?
are you maintaining office hour or not?
Yes, of course. We can do office hours whenever you want.
Okay, thank you.
Okay.
Are you available now if I need to ask you some question about the problem of chapter 14?
Yes, of course.
Doctor, I want to ask, where are you uploading the
At the end
recording?
of the YouTube playlist, you have I posted all live sessions we did together.
Okay.
At the end of the list, it's called F24 MEE241 and parts 1, 2, 3, etc.
Okay, doctor, thank you.
Okay. Christopher, let me
Yes,
open chapter 14. You told me chapter 14
Yeah.
problems.
Yes, review problems.
Yeah.
Can you leave
Thank
the
you.
session?
You can leave if you don't have questions. Okay. Dynamics. chapter 14, review problems. So it's here. Yes, Christopher, tell me.
Yes, I do have few questions and many problems, so if you don't mind.
You want to open a new meeting?
لا fine بس إني يعني بس كم سؤال صغار يعني
يلا tell me which problem?
Okay, in exercise 2,
Yeah.
the L for the force of the spring.
Yes.
هلا نحن in the problem we did AC minus BC.
No. Please pay attention. AC minus BC is for displacement of F. Okay?
Yeah, that's right.
But for the spring, what is delta L? It's initially
It's
unstretched.
SB.
It's SB.
Yes, SB. True.
Yes.
True. But yes. So سؤالي ليه ما كان BC minus AC مع إنه delta L هي final minus initial هي AC.
No. Delta L of the spring. يعني initial, look, this is the initial length of the spring. And they told you it's unstretched. What is the final length of the spring, Christopher? In this position, your spring is always vertical, no?
True.
So what is the final length? It's this distance. What is the difference between L final and L0? It's SB.
Yeah, true.
So delta L is SB.
Yes,
of the
and
spring.
if we want to talk about the F, the force of the cord applied on the cord.
The force applied on the cord will cause a displacement, a vertical displacement.
True.
And this vertical displacement is due to the change in the length of this part of the cord. But because the total length of the cord is constant, the increase in length of this part is equal to the reduction in length of this part. So to get delta L here, you need to subtract. You need to consider this length minus this one.
Yes, the question was why AC minus BC and not the inverse? Because can't you apply?
AC is larger than BC, and you are moving downward. So this length is increasing while this one is decreasing. يعني delta of vertical part is minus delta of small part. Because you have small L plus big L equal constant. They vary in opposite ways. So the vertical length big L will increase, the small length will decrease.
Yes, that makes sense. Thank you.
Okay.
My second question is in exercise 7.
Yes.
Just when we take the video of the girl and the cord and the girl sitting on the swing.
Yes.
Why don't we consider the normal that the swing makes on the girl?
Because you considered only the girl, or you considered the whole system?
No, and I consider the girl with the tension of the rope and her weight.
Okay, because look, the girl is taking, this is your system. Okay, this is the cable, and this is the girl. Okay, you can consider you have the weight of the girl, and you are taking the chair with the girl. The chair is with your system. Okay, so you consider the tension acting on both of them.
So as they are one.
The normal between the chair and the girl is internal to the system.
Okay.
Other question?
Yes. In exercise 14, the last one.
Yes.
So we were saying that K delta SB minus K delta SA equals 0. Is it because we applied that?
Because of action reaction, principle of action